Well, firstly, thank you very much all for your talks. That was really, really interesting. And I think it would be really, I think there was a lot of discussion perhaps of machine learning. And I think, Ingmar, what you left us on fast and slow resonates with a lot of talks, from Helmut for your idea of this kind of low level, perhaps that's our reflexes or our intuition, from all through this idea of kind of repetition and trial and error, and even from Guing, your idea of the learned model and also learned-based reconstruction of soft robots. So I wonder maybe if we could start by having some discussion of this fast and slow approach. How do we combine that with, does it combine with this idea of embodiment, and how could we share these tasks, and what should the role of machine learning be in this context? I don't know who would like to start us off at all. Maybe Helmut, it's good to come back to you because of your initial thoughts on this kind of really low level front end in hardware.
Yeah, sure. Thanks. Yeah, it was great to listen to Ingmar. I see myself reflected in there. Although obviously I'm working on the lower end, on the intuition, on the morphological side, but there's, I mean, there are many more layers in big biological systems, but I think it's a really nice approach to think about that. Maybe I could also introduce the concept on the morphological side on slow and fast there as well, without going up to the higher cognitive functions. Because we often think about, okay, we have these physical systems, they're working in an analog kind of physical space, and then you have a digital computer, and how can it be actually some kind of communication going on without getting rid of a lot of information? And I think one way to think about it is, from the perspective control theory, is that you can have an analog system, and then you have limit cycles and a switch between different limit cycles, and suddenly you get a discrete space where at the low end you're still analog dynamics, and the switching happens less often than the actual dynamics. When you walk around, for example, then you switch and then do something again. So you already at this very mechanical level, you get this slow and fast working together. And this concept is used in control theory quite often, right? Where you have separation of time scales and frequencies. So actually you decouple them and you can control them separately. And this is also not just in time, but also I think in space. We don't think enough about scaling up systems to have like millions of sensors, and or working at a molecular level up to macroscopic robots. I think there's another scale that has to be considered as well, and it's definitely connected to slow and faster as well.
I wonder, Ord, again on this fast and slow thinking, how does that fit into kind of the frameworks you're approaching, and do you see again the advantages potentially of this to kind of temporal scale approach?
Yeah, it's a complex concept, and first I want to thank Ingmar for bringing this up and giving us a little bit of a spectrum of all the different questions that underlie this distinction. And to follow up on what Helmut said, I think there are different types of slow and fast. The one that we've looked at so far was essentially mimicking what humans do, and that's when they search for a solution, it's slow in the sense that you search, and once you've trained yourself, then it becomes automated and it becomes quicker. And I don't know what we mean exactly by quicker, because it's quicker in terms of that it doesn't require to search for the solution anymore, but the motion may appear for an outsider as being as slow or as quick as it was before. As for the switch, and that's what you just said, Helmut, but the switch between different dynamical systems, cyclic versus, let's say, point-to-point, one thing that fascinates me in the way that it's controlled in animals, and you can also do it in control theory, is that you can actually have those switches completely smooth with no different time scale. Think just of bifurcation. Now you can bifurcate from a limit cycle system to a single attractor point, and it's essentially changing one parameter. So I like your concept of the different time scale for the different types of sensor, and maybe I'll pass on the ball to Young Lee, because this is exactly the issue when you control for tactile sensors. I mean, there is a wealth of information, same for vision, that if we were to really process all of this information at the same speed as we process the control of each of our joint, we will never go about this. And obviously, even for robots, we tend to do this processing much faster, either by computing a reduced information, using a little bit of attention, something like this. But this is from the computational viewpoint. So I wanted to hear you, Yongli, if some of this reduction of the dimensionality of this vast information that will allow for it to be tractable can be done at the hardware level, and if there is anything that resembles what is done in animals, that somehow we know that we're not looking at every single information from our skin. We tend to pay attention to different areas. So to which extent could this be hardwired to simplify this computation and to make it faster as far as a computer is concerned?
Yeah, it's really hard questions. Yes. So if you increase the number of sensors, you need to process a lot of signals, a lot of information. So that's really hard. And then that burdens the systems. But sometimes you may be able to think some levels of information. So you can categorize the levels of information, and then depending on the levels of information, you can have different processors. So for example, we have brains, we have a brain, and then we use brain to do all kinds of physical activities. But sometimes the signal doesn't go to the brain. There is a reflex system.
Yeah.
It doesn't go to the brain, and then it only just responds from some low levels. So maybe we can have divide the signals and information with different levels, and then depending on the levels, we can have different processors, more advanced and complex processors, and really simple but fast responsive processors. So I think that is one way to process all these different a lot of signals if we increase sensors and actuators.
And maybe
one issue. Oh, I'm sorry, Josie.
Please, Aude, go ahead.
I was wondering, you know, when you simplify this computation, imagine you simplify it at the hardware level, or you automate it the way that we see it. One issue that I see is when you want to go back. When you want to go back and revisit the representation or revisit what you've learned and add new skills. Can we? Yeah, I think Helmut wants to jump in.
Helmut?
You're muted.
I didn't want to interrupt you. I just want to follow up on that.
Okay,
you haven't finished, have you? What? Have you? Okay. I think one way to solve the morphological space is to use physical reservoir computing, where we do exactly that, where we have this kind of signal coming in, and the morphology is expanding it to a huge space and then reduce it again, right? And while it looks like we open the space to much more information, actually you can pick and choose the right small information in order to do some kind of computation that you want to do. So for example, we did something where we have like a silicon-filled channels of water, right? And then we don't have pressure sensors like in a grid, but actually we have random channels, and then you just measure the resistance of these channels from the outside. We have different pairs. So it's a much lower kind of space that you're looking at, because the morphology is warping the information in like a machine learning kernel, this high-dimensional space, and then it's very easy to use very simple learning on the readout, even linear regression, in order to learn the mapping from what happens to the actual changes in resistance or impedance, for example. So that their morphology can help there a lot, and we see it in biological system also, that there's this kind of large space, a lot of sensors, a lot of really bad sensors, a lot of noisy sensors, but then there's this neurological layer that works together and picks out the right signals in order to get the task done. And this maybe also answers the question about how can we go back. Well, if we can relearn, because we have this kind of morphology maybe stays the same, but the readout is adaptive and can learn a new task and pick out different kind of signals. It's this kind of potential of different kind of signals, and then they pick and choose basically what is best. That makes sense or not? No.
I don't know. Do you have a concrete example when it happens that the brain is actually revisiting this and changing the representation?
I wouldn't say the brain, it's more on the lower level, right? So obviously there are neurons, they're able to learn. And we're not talking about just the brain, but really the ones who are closer to the actual sensory system. So for example, on insects, you have a lot of different hairs and they're different size, they're different thickness, different stiffness, therefore different length as well. And they're all connected to sensory, but it's not that it goes through like in the sense that I read out every single sensor and then I make up the model of it, but actually it tries to get this information and then there's some kind of information flow cooperating it together. And the way how you mix this information together depends on how good this information is. When one of the hair breaks off, this information is bad, right? Or if the sensor is broken. And that's a very different approach than what we're currently doing in robotics, where we have few sensors, very specific ones, very expensive ones, very precise ones. But if they break, the system completely fails.
Ingmar, maybe coming back to you now, what do you think about this kind of physical level of computation or filtering or kerneling?
You know, I love the notion of embedding as much of the computation as we possibly can in the hardware. I think when Helmut talks about where the line is, I think that's exactly the right question, right? Because not all of it is conducive to be baked into hardware, right? And so where is the line? I don't know, because I don't really deal with that part of the space. But going back to something that Young Lei said earlier, in the context of having a lot of information coming in, you know, whether it's from high density tactile sensing like skin or anything like that, it's not different from having, you know, millions of pixels coming in from images, right? And for me, one thing that has helped us a lot in the past is looking at that literally as a compression problem, right? And that is the direct connection actually between some of the stuff that we've done and some of the stuff that Urs talked about around the sort of the manifolds that exist, where what we found is that when we compress some of that data, and specifically imagine that you're only encoding, for example, feasible states of a complex robot, which is literally what we've done. So imagine you have a manipulator, you really only encode feasible states. So all your training data is feasible poses of your manipulator, right? You encode that. You end up with a structured latent space. And if you use a generative model, there's sort of two things that are exciting about this. You end up with a structured latent space in which you can interpolate in that space in such a way that you get feasible trajectories out. Okay, so one of the things that we are doing in terms of planning, which is super simple, is literally train on static poses of feasible poses of manipulators. And then we're saying, well, actually, we do gradient descent in that latent space, and every time we decode that back into a pose, we end up with a valid, with a kinematically and also dynamically feasible trajectory, right? So that's a super exciting thing to us because it's a super simple way of learning stuff and sort of executing it. The second thing, and that goes back to a point that Helmut made earlier, which I also loved, about the body constraints, sort of take into account what your body sort of feels comfortable with and sort of exploring in that space. If you do that same thing with a generative model, what you can do is literally encourage motion through that latent space in areas of high likelihood under the training data. And your training data in this case were feasible states, right? And we find that massively robustifies the entire approach in the sense that we no longer get stuck in local minima. So we have, you know, ample evidence that works on manipulators, that works on real-world quadrupeds, like the video that I've shown. And if I went into any detail, sadly, I don't have time to do that now, but if I went into any detail about the simplicity of the training data that we use for that, you would be in all likelihood blown away. I know I was. I didn't think that would work, but it does. So that sort of connects to some of the things that were mentioned here.
Thank you very much. So maybe that really puts on it, this idea really turns on our head, for example, what is a good sensor? Or what is a good actuator? We need to rethink, for example, Young Lei and Guoying, you talked about sensors and the design of these physical structures. We no longer want sensors that have a nice one-to-one mapping between input to output, perhaps, but we want to say, how can these best shape or filter the data? So maybe it's also, if we need to talk about learning, we also need to talk about at the hardware level, what is an optimal design for perhaps this kind of for machine learning or fast and slow thinking. Young Lei and Guoying, I wonder if you have any thoughts more at the hardware level. How do we define a good sensor? Because when we look at what Ord shows with fantastic capabilities with the sensors we already have, but where do we need to go next to improve capabilities?
Okay,
Yes.
thank you. Yeah, okay. You first, yeah.
Okay, yeah, go ahead. Yeah.
Please go ahead, Goyang.
Yeah, thank you. I'm not very familiar with the machine learning, but I remember when I first do the software robotics. I remember when we use the traditional rigid robot. For example, when we took raster object, we were very accurate to control the joint position of the finger. Then we can too easy to handle the object. But when we want to use the soft material and soft structure, we can see that even we didn't have a sensor or have some very complete algorithm, we can very easy to finish this work. But when we want to do very fine manipulation, for example, like the in-hand manipulation, even without the sensor, just use the software manipulator, we can also do this. So in my opinion, maybe the mechanical intelligence, like the animals or like the human, he can do some control and also to embed some maybe kind of low level controller or some the located controller. He can to finish this, but when user software robots, we will find this will not easy to model his configuration, not very easy to model his dynamic behavior. That's the reason why I would like to see it will be better to develop a very good model for this kind of the robots. But when we model these robots, if we didn't have a sensor, we cannot very easy to finish the closed loop controller. It's the reason why currently the people want to use the many soft sensor embedded the structure, use the embedded sensor signals. He can to finish this work, but currently we found that the sensor is not robust like our rigid ones in our conventional robots. But how to address this challenge, I think it will be a reason. I would like to think we can use the machine learning method to combine that with some discrete sensor, not all the continual deformation of the structure. We need to use the sensor information. So that's the reason I would like to think we should first to use the physical model and then to combine the machine learning algorithm to compensate some amended part. It will be better to give a very accurate control or some work. Okay.
Yeah. No, thank you very much. I think that is a very good point. And Yonglei, any thoughts again on, in the context of machine learning, what is a good sensor?
Yes, that's an interesting question. So I don't know if this is the right answer, but since we get a lot of information, but we don't process all the information in the same levels. So sometimes we have dominance of information over other information. So for example, if we watch movies, visual information is most important, and then we don't care too much about other information. But if we woke up in the middle of the night, and then if you try to find the phone around you, and then you don't really rely on your visual information, you use tactile information, right? So if we can realize those kind of systems in robots, maybe we can simplify the processing time or processing the complexity. And also, if we think about the creep of your skin, you wear the clothes, but now you don't really care what kind of tactile information you are giving by the clothes, because you wear a long time and then you forget, even sometimes you wear your clothes, right? So those kind of things we can realize in the level of hardware. So sometimes we use some unnecessary information we can reject, and then necessary information information we can reinforce.
Thank you. That's a really interesting point, and some really nice analogies there. Any other final thoughts from any of the other panelists at all? Ord?
I think there is a question on the chat that someone may
Ah.
want to take, because I'm not sure we fully reply to the very question of what is a good sensor and what the metric would be. And I don't think I have an answer, unfortunately. So hopefully someone else can answer. But I just wanted to throw out to all the audiences. I would love to see sensors that are very different from what humans can do. Sensors can see through. We start having some of these that can see through cars and see the next car, for instance, but it's only one car ahead of time, and it's not very good. I would love to see sensors that are based on sonars, for instance, that could actually test for the texture of the object without touching it. Just poking it with small sound that are not necessarily audible to us. And to see the resonance of the tissue material before you actually go and grab it. And if we could just go beyond the human and think in that sense, I would love to see that and to use those type of sensors. But yeah, back to the question in the chat. What is a good metric for a good sensor?
Yes, and any other thoughts? Maybe just Ingmar or Helmut, what is a good sensor? Do you have any thoughts, both from a characterization of the sensor level, and also is there something we can look at in the latent space, the machine learning space? Any quick last words on what could be a good sensor?
Yes, I agree with it. It depends very much on the situation, right? What you're looking for in a sensor. If you need high precision in an assembly line, obviously the current sensors are exactly what we're looking for. If you need robustness, redundancy, we have to think differently about sensors. I think scaling up would be then the way to go. Have a lot of sensors and have some learning in the background.
Thank you. Ingmar, any final thoughts?
So to be honest with you, for me, a good sensor is one that is super low power and like a torrent in terms of data. So if it's a sensor array, which I think the question was about, like, give me as much data as possible, because I think one thing that we're pretty good at now in software and via learned models, for example, is the compression. So I'm pretty happy with that. I think it's more challenging to say, high density, large area. How do we even create the bandwidth to get the information to the model, right? So it's that sort of thing. So for me, it's more about the information routing rather than dealing with the information riches.
Brilliant. Thank you very much. Well, thank you very much to all the panel for really fantastic talks and really interesting discussions. Thank you very much for being so involved, because it makes it really interesting for everyone. And I think there's a lot of interesting questions that have been raised, and also lots of questions to answer. And I think Ord's point of can we go beyond human sensing it's a good question and a target for everyone. So I'd just like to thank you again once more. And now we're going to move on to the lunchtime breakout rooms. So we have then again got 2 breakout rooms, each with 5 talks for the next hour. So thank you very much to our speakers, but I would like to open the breakout rooms and also to invite you to please go and join our breakout room speakers. We will also now show the breakout rooms on the screen, so you can have a think about which room to join. And then we'll start back again at 1 o'clock GMT time with our next plenary. So thank you again to all the speakers and for an excellent session, and we'll see you again soon. And please enjoy the breakout rooms.